Good evening, everybody. So, for the past couple episodes, I've been working on this machine I call the B4 virtual machine, little CPU, and or emulator for a CPU. So far, I've got an implementation in GD script for Godot, the Godot game engine, and another in Pascal. And I also have an implementation in J that was at a different, it was done years ago, several years ago, months ago. At various times, I've been updating the spec. And so now I'm trying to bring this version in line. And not only do I have a spec for, or at least a partial spec for how the thing works, but there is also a test suite that allows me to run test first and basically interact with this thing through a command line debugger. So the J version did not have that. So that's what I'm working on today. So I want to bring this in line with the other versions and also get this debugger working. And I took the Pascal version, so b4i.pas, yeah, that I worked on, I guess, yesterday. Maybe I'll shrink my head down here now. And basically, I've just, it's maybe 100 lines of code for the shell around the virtual machine. That allows you to interact with it from the command line. And so you can enter commands like, you start the shell and you've got like a little REPL here where you can quit, you can step through the virtual machine. I don't actually have a button to say run, but that would be the, probably %R would be run. You can query the data stack and the control stack. There's two stacks on this machine that just contain data. And then there's an instruction pointer. And so you can query those things, and then you can do like direct. You can do both assembly of using. There's a particular function up here that if you start the line with a exclamation point and an address, then you can write to RAM, and that uses the syntax of the assembler. So you can actually assemble things directly into RAM. And then you can also read what's in RAM with the @ sign here. You can read a chunk of RAM. And that's all done with the command line. We'll see how that works in a second here. Anyway, so J has J is a very odd language. You can see some of the code at the top here. So if you want to read a line of text from standard input, this is what that looks like. This is the definition of that function. It's basically this exclamation point : is a system library, and so like the one on the left is like a group of system commands. So it's like group 1, and on the right it's like function number 1 of group 1. So one has something to do with group 1 has something to do with input and output, and then there's like a 0 and a 1, like read and write and all these things. And then there's also, when you fire up J, there's an interpreter running. So you're normally typing into the J interpreter, but there's a notion that I believe is called the latent expression that, I believe what you do is you tell it that when you're done processing the script, this is what you want to do instead of the J prompt. And so I believe 929, bang : 27 is the function that, it's in group 9. And function 27 is the one that sets the latent expression. So you give the string and it tells what to do. And then after that, 929, I believe turns it on or something like that, or maybe vice versa. Right? Actually, it looks like. Oh, right. So 929 turns it on and off, and we're passing it a 1. The 1: is a constant function, and so we're passing that to the to this function that turns on the thing. So set the latent expression, and then this left then says, or this left bracket says, okay, ignore everything on the right and instead do what's on the left, and that's a 1. So then the next step is passes to this function. So you can see J is a very odd language, right? But it also has a way of defining. These are called tacit definitions. where you don't see any variables. You don't see that there's an argument called y over here passed in. You could do it that way, but I guess in this case the argument is ignored. It's because it's empty, and then in this case the argument would be the string that we want to do. So in this case we want to do main, and again we're passing in an argument even though it's ignored. So this is like the sign for infinity, but I tend to use it as a default argument for things. Sometimes you also use like an empty string, but since it's in a string, that would but then, so what it's going to do is it's going to run this, because I have do next here, it's going to invoke do next and say run this string instead of showing me the J prompt after you process this file. And the rest of the file is just definitions. So we got definitions. We load the G4 library that has the actual virtual machine that I did some time ago, which is out of sync with the spec, and so that's what we're going to update. And then these are some things that were in this Pascal version. So if you look here, like put mem, so I've defined some function to like parse that input string and put it into memory. And so instead I just left this. This is it's called the cap, but basically if you pass it a function, or if you pass it an argument, it just gives you an error. Yeah. In this case, what it says is don't pass in a function on the left, right, or an argument on the left. So it marks this as being a monad, a single argument. Whereas here, just by itself, it just says, it's not implemented. So I use that as a notion, as a convention for things I haven't implemented yet. So it's a stub, basically. So the idea is that in this session, I'm going to have to implement these things. So dput needs to talk to a virtual machine and put it on the stack, and so on. All of these things are going to have to talk to a virtual machine. Okay, but this explicit language, so that's the tacit language. Now here's inside these curly braces, double curlies, I'm defining a function or a routine, whatever, that takes, in this case, no argument. But you always have to pass in 1 or 0 arguments. So it's a monad that just ignores its argument. And we're going to do all this stuff. And I basically just copied it directly from Pascal. And it's very, very similar to language, and in terms of just like imperative stuff. So while one do something, well, I'll not, I guess I changed the algorithm very, very slightly. But basically read a line, and I define read line upstairs or there. I call it line instead of string over here. And I'm saying, well, okay, if the first character is a exclamation point, then we're going to call this put mem function, and we're going to pass in the rest of the line here. Here I pass in the whole string. Otherwise, for each one of these tokens, so we're going to split the line on the space character. So here I say split strings in Pascal, I do that, and then here in J, we just say for underscore and then the loop variable. So that defines it. That's basically like saying for token in something, just like for token in split string. Do, and then our do. And then we're going to say what all these things are. So here I actually have a little debug output just for myself, just whatever is the token. And then I expect that token to be in a box, so a boxed string. And I'm not actually sure that that's the case, but we're going to find out. And then we're going to select. Actually, I know I expect that because I had a ver tangent labs j refl.ijs. So I had this little demo that I did like years and years ago, and it told me that. Oh, I see. It actually does box it or something. I'm not entirely sure what that is. So this says read line, then put it in the box. So I was explicitly putting it in a box, and so probably this is not a, it does not need to be unboxed. But in any case, I had this thing that was demonstrating how to do all that stuff I already described about setting up the thing. So I guess I was expecting this to magically box things for me, but it does not. So I just have a string, and then now I break that into smaller strings, and then for each one of those strings, then we just compare the string and we'll see what it is. So actually split string might, well, we'll see. I think when you iterate through it, you get the individual items. If not, we'll find out. Actually, it doesn't hurt to have this here, so no matter what. It doesn't really matter if it's boxed or unboxed. Let's see. Then I just stub this out. So rather than actually showing the data stack, I just printed out an empty data stack, and so it's going to fail the test when it actually wants to show some data. And then the IP address starts at this address 600 or 256. That's a hex number. And then that's those. So we need to actually look up the program counter or the instruction pointer. And otherwise, if it's none of these tokens, then we inspect it and we try to assemble it. So it can be a space quoted character. It can be a backtick quoted character. These basically put in literal bytes. These put in ASCII control characters, or actually they put in each ASCII control character has a corresponding register in this virtual machine, and so it puts a pointer to that register on the stack. So basically, the first 32 bits or 32 slots, 32 chunks of 4 bytes in memory can be addressed that way. So we have like a dictionary mechanism built into the assembly language. And then the @ sign is again for dumping out some chunk of the memory to the screen. So it shows like 16 bytes out of memory on a line. Otherwise, and then we see here put hex token. So that basically means to run the assembler. Oh no, sorry. That means put an actual hex value. So parse the number, parse the input as a hex number, and if that's okay, then then you're good. Otherwise, we don't know what the token is. And then I skip this line up here, which is these 2 lines. So if the string is empty, which I don't think does anything. Oh, it's because if you had a multiple spaces in a row, then this function would give you just empty token. And I guess I could put the same thing here. So we'll see if we need it. And then otherwise, right before we do this select on what the token is, we probably want to say, is it an operation that we know of from that the assembler is aware of? And if so, then we're going to execute that assembler. So so in Pascal, this is basically assigning the op. This is the input is the string, and then you get back the op as an output. And then it returns a true or false. And if it is a valid operation in the virtual machine, then the function returns true, and we run that operation. Otherwise, do something else. So I need to port this line right here over at some point. But I'm only going to do it when the tests tell me to do it. So I kind of jumped ahead a little bit and just wrote the skeleton of this, and that's where I'm at right now. So yeah, so that's J. J has this nice little procedural language in it, the direct definition language, or the explicit definition language. Has a very similar feel to Pascal, not quite exactly the same, but you can see like there's almost a line-for-line correspondence. And having to use a while loop here and not a and a flag versus just calling exit or whatever. Okay, that's enough rambling. That's where I'm at so far. I guess I haven't really talked about what B4 is. If you haven't seen the other videos, don't worry about it. You'll see it very soon in this stream. But I should say, just to catch up anyone who's been following the last couple videos, we have in the B4 repositories is on GitHub. It's tangentstorm/B4 has all this, and I have some B4 tests.org. It's just Emacs org file that contains a bunch of little tests. So this line is an input line, and so we're inputting an actual number in hex and an actual number in hex. So 10 minus 10, 5, and then we're saying subtract, and then we're going to inspect the data stack. So presumably this pushed the number 10 onto the data stack. This pushed the number 5 onto the data stack. This ran subtraction, and then we inspect the stack, and then we quit, and that should cause this to print out, and then the program ends. So like if that test passes, then it means we are good. And I have a function, a program now that will, what's it called? So I say jb4.sh, and that invokes a test runner that I'm working on. It's not, I mean, you can read about it if you read the file about here in the stuff. I'm not going to talk about it right now. The test runner, I'm kind of turning into something that you can make this kind of like a game that you can implement it yourself. And so it looks like I've somehow broken this. And it looks like the way I broke it is I call co-create, and that is not the right way to do things. Co-create actually takes arguments on the left, and we say b4 co-create, and then an empty list of arguments. So presumably, all right. So if we go into b4.ijs, this looks like a very small file, but it's actually, I've got some control characters in here to break it into pages. And the first page describes like the machine. So we've got program counter, groups, registers. I don't know what the group means anymore. I think it has something to do with UTF-8. We'll get to later. We've got some, in this version of it, I had 3 explicit registers named X, Y, and Z, and then I had the 32 character register. So that's probably going to change because these have now kind of been absorbed into that thing. So the characters all have names, A through Z, and then there's a couple punctuation ones. And well, X, Y, and Z are also character registers. So yeah, I kind of rethought that since I worked on this version of the machine. So these are going to have to go away. And in fact, these are now not really separate items, but they're in memory. So I may play around with that a little bit. It doesn't really matter. Like, you have a lot of flexibility of how you define the actual machine, like where you put things and how you do it. The only thing that matters is if it acts as if it's this virtual machine. You have a lot of flexibility in how you actually organize them. Here's your data stack. This is the return stack. It should be called the call stack or the control stack. So it should be a C, but of course that C is taken right now. Maybe this should be an A or something. And then user adjustable memory. So this is your RAM. In fact, maybe this should be R. And then end is the length of the RAM, and then this function returns just an empty array. That's a 0, 0 reshape of 0. Anyway, so this new function, I believe, the way J works is that if you have O is a locale. I forget what the classes and objects, what the CO stands for, classes and objects. And the locale system allows you to use, define. So basically, a locale is like a namespace, and then that namespace can be, is also part of, the concept of namespace is also part of the concept of object-oriented programming in J. And so concurrent creates a new namespace, a new locale. And then if you have something called new, then that's what gets run when you do this. So when you say b4, which is the name of the namespace, concurrent b4, and then and then we're saying co-create, and that calls this new function. So first of all, it creates a new namespace that is the object, and then links it to the b4 namespace, so that you inherit everything from b4, and then you can override it, and then calls new with this constructor, or with this argument on the right. And you can see that the argument is called y. Left argument, you can only have 2 arguments. You have x on the left and y on the right. And in this case, we only refer to y, so lowercase y. And so that's an argument on the right, and this is a monad, right? So this curly braces look at everything inside there, see there's only one variable referred to, and that's the lowercase y, so it must be a verb that has a function that has a right argument. Right, so that's the definition of this so far. And the actual definition is these are all zeros, and then 32 shaped 0 is just 32 zeros in a row, so an array of 32 zeros, and then the return stacks are arrays of numbers, but they're empty, so 0 shaped 0. Okay. Here we have a 2-dimensional array, the actual result of this. This is a convention in J of just returning nothing. I think it's actually predefined to be empty. There's a name for that. Anyway. Okay, so let's run the test. I don't think in my tmux here, I'm going to keep this tab open with these two so that I can pull more stuff from the Pascal version, so I don't have to think too much as I go along, because heaven forbid. And here we're going to run the test, so we're going to call this tests, and let's go ahead and run it. And I did run it, and co-create is wrong. Okay, so maybe it's been a while since I did jsoftware.com. Co-create. Maybe it should be co-new. Find out. Let me bring this over here. I am not fluent in J anymore. Spend some time. Co-create. Create an object. Yes. You click on it. Create. Maybe it's co-new. Create object. Create object. I bet co-create. Here. Shut up, Bing. I don't want this. Locales. I think it's co-new is what I really wanted. Okay. Yeah, so co-create is just creates a new space. Right, so I actually probably wanted co-new. Well, I'm just going to call it. There you go. Okay, so we got past that function. So okay, so I guess let me explain what we're seeing on the screen here, so you're oriented here. This file is what's being run. So when I run this, let's actually bring that up. JB4. No, but it's actually in LearnTris. So the test runner is written in Python, and I actually started it for a long time ago for a project that gives you a test suite for Tetris. I'm going to talk about in the video soon. So the test runner is actually called Tetris at the moment. It's going to have a new name soon. But I've made some extensions to that to let me run any variety of tests. And so that's what this is doing. So basically we tell it where the test plan is, and then we invoke our interpreter, and then it runs the tests. And what it does is it parses this org file, and it looks for anything that looks like this, where it says begin source, end source, and has a name in front of it. And then inside of that, it looks at the lines here, and each line, if it's this, if it's a greater than sign, it's a this is the line of input. This is like, and then the rest of this comes up on the screen. And so in this case, there's no output. But the idea is that you run the tests, and then whatever fails, like here, this very first test has failed. And so it says test Q failed. So here's the name of the test. And you see it here again. This test has failed. Here's the input that we sent, and we sent the string Q. So you see here this line has a greater than symbol. Here it doesn't. So here's what we sent in, and then now it's telling us what do we do. So all this over here, all these lines with colons in front of it, represent the text on the screen, right? So basically, this is now a prompt for you to pass this test, and then here is the difference between what we expected. So this is a diff between what you output and what actually happened, and you can see that so these lines need to be these lines have a minus sign in front of it. It means you need to get rid of these lines, and then here, if there were lines that you needed to add, they would have plus sign in front of it. Yeah, actually, this is kind of reversed, right? This is not the diff from expected, but this is the diff between if you type like diff expected, and then actual, this is what you would get. So this is like how you would migrate from the actual, no, sorry, diff actual expected, right? So it's actually opposite. Diff, yeah, I need to reword this. I should reword this so you can see what it, whatever. Anyway, these lines need to be, this is like a patch. This is what, this is, the word should be a patch. This is the patch you would have to apply to your output to make it match what the output should be. So you need to remove these lines. Okay, and then, so we'll do that in a minute. And then here, if we had managed to pass this test without spitting out any errors, then the next test would run and it would say, well, you need to have this. And actually, this is a comment in the test language. So this is the actual output, which is why over here we say print ds is pass that test. So all these first couple of tests should pass. And then that's it. That's all the tests do. Is you read lines of input like this. The test runner sends these inputs and expects these inputs. And if you don't get those inputs, then it says that test has failed, and then it stops running the test and it just runs them in order from top to bottom. And if you get through them all, then it says, however many tests passed. I think there's 37 of them. We're passing, 0 tests passed here, test 1 failed. I should really remove this number because people say in the LearnTris repo, like several hundred people have gone through here and worked through the test, and they responded with like, test 7 has a problem. But if you look at here, there's no number 7 anywhere, right? So you don't see a number 0 in any way associated with this. So really, it should only be this identifier here. So that number should go away. Okay. But I will do that another time. There's already a ticket for that that's been open for like 10 years now. I haven't worked on this for so long. Okay. So next step. So we're running this test. Everything's working as far as the test runner is concerned. It's able to launch the program, but we got this error, a length error. So why are we getting a length error? Somewhere in b4i.ijs. So let's just see. I actually have the I actually have some links to it, so I don't have to keep changing directories or whatever. If I just say b4.ijs, oh, b4i, sorry, right. That makes more sense. Okay, so somewhere in b4i.ijs, I'm a little confused by the stack trace there, because that is not the, I actually do want this. I want to preserve this view of the world and just run the tests. So this one, and then over here, let's open a new one. cdjlang. And let's say b4i.ij. And we got that error. Emacs ver b4jlang. We'll open it. And I'll switch these around, and we'll bring that up. Okay. So why do I have an error on line 1, 2, 3? This one? Is it backwards? Is it this way? Yeah, it's been a long time since I did object-oriented programming in J, or even work with J at all. So, but this writes something in a namespace. This actually refers to a variable called VM. So we're going to make one instance of the VM. That's what I'm trying to do here. And I don't remember how to do that. So rather than fiddle with that and try and look it up in the docs, I'm going to look at my own code where I know where that is. So if I look at JPrez, then I will very quickly see how you do that and bring that back. Maybe I will. See where? There we go. I'm making something. Yeah. So new and then okay. So it's the class name and then new and then whatever. And then if I actually want to look at that, I would have to look in the jkvm directory. How about jkvm? And then under UI, there's a bunch of like widgets. So like the editor create. And I think I called it new here and rather than create, and that's my problem. All right, so let's call this window b4.ijs. And actually load that up. b4.ijs. jlang and then b4.ijs. So I think the answer is that this needs to be create. And then, was it co-create? Did I have it right the first time? Let's get rid of that. Go back to this. Co-new. Okay, so it was co-new and create. So I was confusing the two. Right. Co-create, we established only just creates a name. So every namespace has a name, but if you use co-create, if you use co-current and give it a string, it goes into that directory. If you use co-create, it creates an anonymous locale. So that's basically an object, like an empty object. And then every object has a prototype, just like in JavaScript. It's very, very similar to the JavaScript object model. Inheritance model. Just to say it's prototype inheritance. Okay, 2. So I believe now that I have. So I guess you can. What's happening here is that I have never tried to create this as an object. Everything I've done in the J implementation has been just creating variables in memory. So I didn't even use the locale line, the co-current line had been commented out. I guess I could bring that up. So yeah, so if I go here, this line at the top had been commented out, and this was just called new. So I got to find if there's anywhere or new. Yeah, okay. So maybe new is equal to create. Just for use here, maybe we could say create here, create y. New is a bad word, so maybe really it's not new because it's not making a new one. It's just reset, right? Reset equals create. So NB, this is for this would be if you're not using as an object. If you're not using multiple, if you are not using full. Oh, I guess it really doesn't matter. Like if you have an object and you want to reset it, this resets it. So reset to initial state. And that way you could call it on an instance or on the real thing. I actually really like that about J. Said it was like the JavaScript object model or a namespace model, but you can import a namespace. So it's not just a class. It's not that you have an object, but the namespace itself can be imported into the current namespace. Whereas in JavaScript, that only happens if you're like nesting. If you're, I believe, you're only nesting. There is a concept of a default object, and that can have a prototype, so that can allow you to move the namespace around or whatever. But so like in your web browser, the default object is the browser itself. So anything that's defined on the browser object gets, I guess, window is the word. So anything that's defined on window is in the global namespace. And if you changed, I don't know if JavaScript has a way to change that. from the code. It's just the environment gives you that default object. I have no idea. Maybe there is a way to do that. But in J, you can explicitly set, hey, whatever locale I'm in, I can inspect that locale, and I can see how it's chained, right? And so then the object system just kind of falls out of that. I actually really like the way that works. The only thing I don't like is the syntax right here for, like, normally you would write, in some other language you might write commands.w, but instead it's like this double underscore thing, which is fine, but when you're saying like a.b.c, that in J becomes C underscore double underscore A, something like that, which is weird. It's just a little backwards to me. It's okay, but you know, I don't know. Anyway, enough rambling about that. So I like the idea of reset down here. So trace and boot are meant to be, I guess this version has some tools for like dumping out what happens and like seeing what happens. This is meant to be a highly inspectable thing. So I haven't really played with it again in months. The last commit was like 10 months ago. This implementation. Anyway, let's see if this works. So that is because I used the wrong key. I used the wrong syntax. That's Pascal assignment. This is J assignment. There we go. All right, so now you see I don't have two spaces of indentation. I'm in the B4 prompt rather than the J prompt. So everything is working, and if well, actually we can say D and then see the data stack. And it's actually not easy to tell whether that's, I use a semicolon. But if you say, that again, oh, you gotta say quit. I want to see if it's boxed or not. I think it's not. Here it's not boxed, but it is boxed. Okay. Okay, well. I'm just gonna echo the token. No boxing at all. Just as a sanity check here. Yeah, okay, so it's boxed. So anyway, quit. If we just say J and we say ABC split string, no, you want to say space, right? Space split string hello world. Then you have boxes, and as you loop through them, I don't know why I thought I expected them to be unboxed as you loop through them, but you get each box, not each unboxing. Okay, all right, so that answers that question. So split string causes the boxing. Select. I don't need to say what split string does. You can look it up. Okay, so now for each one of these boxes, or for each one of these tokens, look at what's inside. If it matches one of these things, we just saw that Q quits. So if we come back here, Q should quit, and this test should pass. And if we run it, you see that it did. So 3 tests passed. We actually fast forwarded all the way down here because I implemented showing the empty display stack, or the empty data stack, sorry, and the empty call stack with question mark C. So those work, and now push a hex number onto the stack, and it should print it. This is a little redundant, isn't it? Like here, push a hex number onto the stack, and then here you give it a title here. Maybe this should just be the title. I'll probably rewrite the test to indicate that. A little less verbose, and maybe even put the name, which is IOHEX over here, like maybe put it on. There's a thing called tags, so you can say like IO.hex or whatever. Syntax for that. A little less verbose than writing this plus name every time. I wrote these tests like recently, and I found that they were a little cumbersome to write. Anyway, all right, so this is the test that's failing. We don't actually have to look at this. In fact, I'll probably like hide this file and actually bring up the merge these two. So let's bring up b4.ijs. Whoops. Bring up b4.ijs, and we can see what failed over here. So the input should, or maybe even bring up the b4i, the b4 interpreter.ijs. So it should print in hex. So first of all, it didn't push anything on there. So we need to implement dput. It didn't complain. Like it parsed these numbers completely, but it, or rather it didn't. It just came down here. So okay is do nothing. So let's do it like this. If put hex toke do blah blah, and we'll say put hex going to be let's see what happens if in J if we type so if you want decimal from hexadecimal, then you would type DFH. It's a little weird. That's like their word for parseint. ABC, right? That gives you that number. And we say banana. Oh, that actually is. Oh, interesting. That is not good. So it's all base 16. Like, what is DFH? Oh, I see what it is. Any letter that you put in, so DFH N is 0. Right. So AN is the same as A0. Right. Right. So maybe a better version of this would be I don't know if it's a better version, but like to actually names. The J locale has some stuff in it. Might be related to this. Oh. How about the Z locale? I don't think there's a. I think that's the only hex related thing we have. I'm sure that I've written this many times before, but I don't think I have a hex library. Okay, so let's just do is hex, right? So is hex would be basically that they're all. So that's all. So we're going to do a bunch of Boolean tests. We're going to get back a vector of bits, and all of the bits have to be true. So if we say that's going to be 0, but if we say 1 1 1 1 1, that's 1, right? So that's all. Oh, I lost my. So is hex is going to be this. And what do we want to do? We want to know that every item is hex if it's an element of, so we're going to say this and this. So all of this, and it's an element of those numbers. So 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E. And in fact, see, like I have some of my instructions are like that. That's the addition instruction. That's the mnemonic for the addition instruction. Well, that's a valid hex number. So that's why you do the opcodes first and then the hex thing later. But the syntax is that the opcodes are all lowercase, the preferred way to do it, and then the hex numbers are all uppercase. So I'm not even going to do that. So I'm going to say is hex. Wow. Okay, let's do that again. So let's say is hex equals this. I just did, 34. Yes, that's 1. 34c 1, and 34 lowercase c is 0. Now that. Maybe call hex with uppercase, right? Is hex uppercase hex. And I lost the right parens here. Do I need that? I believe that's required. But it's more clear to me with it. I guess it's not required, but I find that a little clearer if we do it this way. I'm a little rusty. I'm rusty on J. Yeah, I've been working in it for quite some time. Okay, put hex. So if we look at the Pascal version, basically we try to put it onto the. First, we try to translate from decimal, from the number to hexadecimal. I'm sorry, from the hexadecimal to a number, and then for that string, and then we put it on the stack. And if it fails, then we return a false result. So I'll do that and say a dput is not going to fail. So dput, let's say if is hex y do dput decimal from hex of y else 0. And we want to do this, and we say return else 0. Or you can say end and then 0. And you could probably write this as like dput dfh. Right, so this backtick so 1 yeah, I don't even want to mess with it. Yeah, I was trying to make it tacit and just for fun. Like, to me, this is much clearer. It's probably slightly slower than the tacit J, but I don't know. I've been kind of going back and forth about using all these symbols. Like I really like the expressiveness of J when I'm putting stuff on the screen and doing a demo and writing code. And I wouldn't say that it's like my code is read only. I think that I tend to put it at a level where I understand what's going on. But I usually can't read other people's J code without a lot of work. And I don't know. I really like the power of the array languages, and I like the notation, but I'm not sure what to do about the problem of keeping it in your memory, right? Same thing with for, which is what this machine is. But I'm a professional K, or up until very recently was a professional K programmer. And K has a much smaller language. It's a very similar style, but where everything is overloaded. But you're, I would say J has, if it doesn't have 3 times as many, probably more, maybe 5 times, 5 or 10 is many more operations built into J than there are K, and it's much more powerful. But it's just really hard to remember them all. And I don't know, it's part of the fun, but like, it's not hard for me when I'm working in J consistently. But it does take me some time to warm up to it again, apparently. Because it's been quite a while since I mean, I use J all the time. Like almost every day I have J open, but I don't do a lot of serious programming in it. And even when I do, I don't normally do the, you know, there's a way of writing a tacit case statement with, I think, this and maybe it's, I don't know, it doesn't matter. It's in the dictionary, it's tie, and tactic is tie, and then evoke gerund case statement. I think. No, I think we have people watching, so thanks for coming to listen to me ramble. Feel free to chat, otherwise I won't know I won't know what you're what's going on, or if I'm making any sense. Or feel free to tell me to get back on topic. Okay. Anyway, so if it is a hex number, then we're going to do all this and return 1. So if we're going to convert it to decimal and dput it, dput is yet undefined, and then return, and otherwise we're going to return 0. So dput would be, I didn't even say VM dput. Backwards, right? So dput VM, right? I think that's actually it. We define let's do this. Let's go back over here and curation as a service. Okay. My private notes on the screen. Not that they're really private; they're just half-baked. All right, so we're going to go into J, and we're going to say we have to. So the path notion in J. So we have to go to. You have to be in that directory, and there is a way to make it, to set it up so that you can have a library that's in a. You have to put it in a particular place if you want it to be loadable as just like load b4, and I haven't done that yet. I have to go to that exact directory, and we go to jlang, and then we will say J, and we'll say load b4.ijs. And I'm just going to copy this. Whoops. So now we have a VM to work with. Let's do. So now we have this thing called VM, and you can see it's at 0. And so if you say names 0, yeah, it doesn't like that. Oh, it does. Interesting. So you can see all these things are now defined in that namespace. It's interesting that I see the double underscore indicates that this should be a name. So it looks in the current namespace in the current locale for a variable named 0 to tell you, you would say VM, right? So in order, because it's anonymous, you would say VM. And that way you can assign a variable that points to any locale. It doesn't have to be one of these anonymous objects. All right, so and to complete the thought, then a locale acts as if it's a singleton object. But you can also make new instances of it. So I use that in the terminal in the JKVM terminal emulator thing. So you have a default terminal, and you just use the commands as you want. But then there's a stack of terminals, and so you can create a new terminal and write to that terminal using the exact same interface. You don't have to say, you don't have to do this double underscore thing. You just change what the current terminal is pointing to, and then the outermost locale has a bunch of wrapper functions, kind of like this, right? So dput is talking to the current VM. Well, you could say push VM or something like that, or push VM. You could make a function like that. It creates a new VM, new virtual machine, and pushes the old one onto a stack. And now you can interact with that new VM virtual machine and then get your result, pop it off the stack, and then that might actually be very useful in the assembler because you want to be able to use use a fresh VM to like calculate things in your assembler. So that's, anyway, I do the same thing with the terminals in there. So you have a stack of terminals, and then the base one is just the plain library, and then each one is a object, or possibly the base one is creates an instance. Anyway, dput VM. So I believe that works now. So if we say dput, so if we want to look at the data stack, we would say d of VM is empty. So if we say dput underscore VM, and we'll put the number 5 on there, then d of VM is number 5, and if we put like the number 54, right? Yeah, there we go. So we're seeing it added to the end, and then if we say d pop VM and then do this, it'll, or anything, it'll take that number off. And then if we say d of VM again, then you see that it's removed that last 343 number, and it just ignored this. That's why you say this, right? The result is the last number, and then it's a stack, right? We're pushing things on. Okay, so this actually worked. So I believe that test is passing now. Let's find out. Pretest pass, it did not. So it did not print in hex. Oh, okay, right. I believe the test is passing, but I'm wrong. So actually, over here, I said, I called this like write stack. So we're going to say write stack. And we're going to say, how about ds? We've got to pass in 2 arguments, write stack, and then d of VM, and then cs, write stack of c of VM. All right, so write stack doesn't exist, so let's make write stack. Write stack is equal to, and we don't know what that is yet. So now we have let's put some text numbers on here. So we'll say 16. Oh, sorry. Yeah, how about we do reset VM? All right, so now d of VM is empty. We can give it, how about decimal from hex, or how about hex? No, decimal from hex. Yeah. 00112233. That work? No. So we have to space split string, and then we say each one. So each. All right, we say every, which is either one. Okay, so now what was the point? Do I want to go in the opposite direction? Oh, right. So first of all, I just wanted to populate the thing. So dfh. How about dput and dfh? So now I would dput VM. Yeah. So now this is the stack. So d VM is the stack. Why did it have a 0 on there? Oh, because the first number is 0. So that's 0, 1, 1, 2, 2, 3, 3. So now, now that I have that stack, I want to say what write stack is. How about we do this though? Let's just make the function simpler and have it return a string, and we'll say echo. So echo that, and then show stack. Stack. right, so which is what I'm trying to do here. So hex from decimal, and we, for whatever reason, the thing is to put a, so we can do this. And we want to do each of them. So under unbox, right? Yes, and then join. No, string join. No. Join string. Yep. There we go. That's what we want. But except we're passing in an array. So rather than call that y, I think we can do this. There we go. Yeah, so that's it. This is it. We only need the part right here. And now that was s stack is equal, let's call it stack string. Stack string. It doesn't have to be. I don't know why I'm arranging them by order of length or whatever. Let's say stack string, that's it. Stack string and stack string. And now that should. Oh, and we need to write we need to put this in front of it, and then on the other side we could either do it like this and put like that, which is fine, and the alternative would be this with that. It's actually somewhat shorter to do it this way, but I think this is, I say somewhat shorter, it's like one character shorter, and only because I use a space. Okay. There we go. That should work. Whoa. Not C, because C is the right. Okay. So right now that is called R. C is the 32 character thing. It should print in hex. Hex numbers pushed to the data stack failed. E. Oh, because we didn't actually push them? Put hex, toke. Put hex. Echo, put hex, comma y. Do it. It should print out now. Main error put hex. Okay, let's try that. Oh, because I split it again, right? I split the string again. No, hang on, wrong place. Token is right. Okay. Let's do it there. Then it's not. Now it's a string. XFF. And you see it did print it out, but it's not uppercase. How do you say uppercase? To upper? Yeah, to upper. Uppercase was like the first major thing I tried to write in J, and I have a whole like I spent like several hours documenting like the experience afterwards. It's called the upcase saga. At some point, I should have finished it because I should have spent more than an hour or two writing because it could have gone even longer. I actually, figured it out and learned how to do it, but like I got caught up on so many like little tiny things, like not knowing how to find a particular word that does the concept I want to do or whatever. Anyway, but turns out two upper is built into J, or is predefined for you. All right, so what am I doing? I am trying to say to upper at this. All right, so now it's an uppercase, and I just have to remove this debug line. Okay, so test 4, or this io.hex worked, and so now we've passed 4 tests. Okay, we went from 3 tests to 4 tests. Now the 5th test is failing, so let's run that again so we have a nice clear screen. Okay, so so to toke. So this is failing because the token is empty. So I'll put that here. So if it's an empty line, we just do continue. We do nothing. Ord is not working. No. Oh! I'm translating from Pascal, and Pascal has 1 base, right? So we Ord 1, right? Not 2. And so this would in Pascal was string 1, and I saw string 2 down here, and I thought that was the second character. No, of course it's a off by 1 error. Okay, so that works. Now we're getting a value error for Ord. So what did I define Ord as? I did the same thing again. So anywhere we see this is a Pascalism. We got to change it to this. And so that was the problem. All right, so that test appears to have passed. You don't. This is not being asked. It's not asking us to remove this, but it says to remove this extraneous output, which is the echo here. So Ord works. Right, so what this is doing is basically if you say just string A, it pushes that, or sorry, quote A, it pushes that character as a number onto the stack. Is that right? So we say ord of A, and then it's in hex, so we say hex of ord of A should be, yeah, so that's right. And so that's it. Okay. Did I remove it? I didn't remove that yet. Okay, so is and I removed this. All right, so we'll say dput for dput quote character to push it directly. Quote character of course it pushes a 32-bit number onto the stack. Okay, so that worked. Oh, yeah, that works. Now we're on to test 5, IO control. This is the same kind of thing and same problem. That's the first token. I could have said, no, I can't. Still failing, and now 168 is better. What am I? Ah, reggae. 4 times OR, that should be right. Oh, but okay, so we have a string. So it's really 4 times 4 minus forward and at sign. No, it's really okay. So we have to say forward at sign minus forward. Back the share backtick equals register address. Yeah, so that passed. So basically, we can see it, right? So if we run it again, a before I to IJS, and if we say backtick A, then it should push like the number 4 onto the stack. 4 times 1. So backtick A is register number 1. Backtick that is register 0. We never refer to it that way. Backtick 1. And then if we see what's on the stack, we should get C4. Oh, no, sorry. Backtick A should be the number 1. Sorry, multiplied by 4 to get the number 4. So each is 4 bytes. That's the first one, or it's number 1 after number 0. So number 0 would be 0. Number 1 should be. So if I say that, then it's a 0. I really like this style of building a little, for whatever program you're building. This happens to actually be a virtual machine, but for any program you're building, build like a little shell for it right off the bat, so you can get in there and interact with what you're doing in your own little language. I really like that style. I really like it for Tetris. I really like it for this, and I'm super excited about it. Okay, so I believe that works. So right, so we passed that test, and now we are moving on to addition. So input. So now we were able to push 1 and 2 onto the stack, and then we're supposed to add them. Add failed silently because the code down here is not giving an error yet. So maybe we should put that. And what does token mean? Or let's say unrecognized op. Unrecognized op. Or unrecognized instruction. Unrecognized word. Unrecognized token. How about that? So I do that now. It should say unrecognized token. And token is so actually print it. Error. Is error built in Word on it? Oh no, it's actually complaining that it doesn't know what the word error means. Error. So print, so echo, and then we're going to exit. So rather than now printing out the number at all, it's going to say unrecognized token and just halt immediately. Okay, so in that virtual machine, so if we just say jb4.ijs, and we say names, and we say co-current b4, so we can go in there and inspect it. And so these are all the things that I've defined in here. Co-current 4. So we can go into that locale and we can see all the names that we defined. And so if we just type create, we'll see the same thing over here that's over here. Live. Why am I telling you that? I must have had some reason. Come back to me in a second. Oh, so we want to, so AD, I think we can say dput like 2, nope. So we have to say reset, dput 2, dput 1. Oh, sorry, I put dput 2, 1. So I can swap, and then I can depop, or zap is actually the word. Zap should be the same as depop. Yeah. Zap. And now if we look at D, we have 2, 1, right? All right, so we want to add those two together, and if we say add, I believe that's all we have to do, and we say add 3, and now D is the stack. So is there a word ops? Okay, so if let's say toke is nothing, so toke, let's say that it's add, and then we want to know if it's an op. So toke, the box of toke is an element of ops. It's true. Whereas the box of the string token is not an element. So is it an op? Is op would be this over here. All right, so over here, again, I'm just kind of like leaning on the Pascal version to like do not rethink something I've already thought through. So something up here is op. So before we do the and now I have to look up something about J. Oh, maybe I don't. Else if, right? That's a else if like that. I think you cannot. Am I crazy to think that else if else is not a thing? Like it wasn't or something? So if it's one of the ops of D, do something. I'm worried this is not going to work anymore, but let's find out. So else if, whoops, it's the wrong place. Probably here. How about, yeah, let's say like if token is one of the ops of D. Oh, we'll just do it like this. We'll just do continue. I don't need an else if. We'll do, again, the Pascal, you can do breaking continue, but I always try to follow Niklaus Wirth's structured programming style, not do continues and breaks. If so, okay. Sometimes I do. All right, so if it's an element of, not D, it's VM, right? If it's an element of the, of the VM, or this list inside the VM, right? List of ops. So ops would be that. Maybe length of ops, 54. How about 60 reshape of ops? What's the factorization of 54? 9 times 6, right? Yeah, so we say 9, 6 reshape of ops. And we get like a little table. And so basically, if it's not in this table, then, or if it is in this table, then we're going to. This is too big. There's things in here that are no longer like not equal anymore. Okay, so that would be right here. If it's one of the ops of the VM, then how do I do that? How do I indirectly execute an op? Current main. We say so we'll make one. So we'll say VM is equal to v4 co new, right, like that, and then our VM is some number, and then we say VM, sorry, ops VM. There's the same thing. So 9, 6 reshape of that, and then we want to say if like I can say add a VM, right, like that, and I get the actual function. Right, so this is like take this and then apply this adverb to it. Basically, it's lifting this J word into the VM, so we're popping and then we're applying the function and to the argument. You don't really need the Y part. Oh, yes, you do. You need it, even though there's nothing coming in. You need that to force this to be a verb. I think. I'm not. I think. I'm not sure. Anyway, so now the question is, I have op equals add, right? So this is what I'm getting at. I've now got a string that has this, but I can't say op of VM, right? That would make sense. How would you do that in J? How the heck would you do that in J? There must be a way to do that. File execution. You could set the locative, right? But I mean, you could say. I guess you could just dynamically do that. Like you could say like, so op is add, so we could say op, comma, and the string VM, right? And then you would have to pass in like an empty thing and then say do it, right? So that now you have this string, and then you want to execute this string, which would be this. Right, so we added them together. So let's do d of VM, right? 0. But let's do d of VM is going to be 2, 1, 2, and then we'll say, and now d of VM is what? 3. So it did the addition. Right, so dynamically execute it, run op. Okay, so that's the way you do it. I think I would suspect there's a other way to do that, but right, so run op would be this, except this is now going to be called you could just do it like that. I think. So where was I doing this? It is op toke. Is op toke. It is op, then run op. Run op toke. Continue. Now let's see if that works. It did. Okay. Unrecognized token sh. And that is because in my virtual machine, I have something called shift right and shift left. So SR is equal to this, shift right. And we are going to replace, I'm not going to replace them yet. This needs to be removed. But I'm going to just, I'm going to break that onto its own line. Actually, I'm going to leave that exactly the way it is, because all three of these are disappearing. There's no more negate. Is there a negate? No, there's no negation operation. You have to just explicitly subtract from 0. I want to do that. And so sh is what we call shift left here. And you would just pass in a negative number if you want it to shift to the right. But it's not a, so ops has to be defined somewhere. And that's a composition of all these ops. And I will go ahead and make the change here. So the changes that need to be made are, first of all, dupe goes before swap. All right, so this is load a byte, load an integer, duplicate, swap, over, zap, dr and rd, which are now dc and cd. Those are the stack ops, s ops here. Just a little more room. The numeric ops are add, subtract, multiply, divide, modulo. There is no more negate, and then we have instead of shift left and shift right, we have just shift. Okay, then I'm going to skip ahead. The Boolean ops are and, or, XOR, not. That's correct. C ops, comparison ops are equal, not equal is not there, greater than is not there, less than is not there, greater than it's only equal and less than. That was hard. That was hard to cut. I was scared of that, but I rewrote my I have a start on a BIOS, and this is able to rewrite that using only those two comparisons. If you want greater than, you just swap the arguments. If you want greater than or equal, you say less than not, right? And then if you want less than or equal, you swap the arguments, then do less than not. So those two are sufficient. And like if you want not equals, then that's equal and not. Okay, and then the register ops. I had one called dx and dy. These were for like independent registers, dx and dy and so on. Sorry, there's these three special registers, x, y, and z, dx, dy. But I got rid of those, so I'm just removing from the list and not removing the implementation for now. Yeah, so this was, y, take from the y register, move it onto the data stack, and so on. I have a better way to do that now, and that is that the instead of registers, they're just actually in memory, but they're just basically, even if you have multiple CPUs, the first 32 addresses in memory are in the CPU. So each one has their own copy of that. And then actually the first 64. So you have 32 named registers and 32 internal registers for whatever you want. And then the next byte you can actually read from RAM. So you actually can't read each version of like the first 256 bytes of RAM are actually uses these registers. So now we don't need a special op for Y for copying from there. We just need one op that reads from memory, which is called read byte and write byte, read integer, write integer. So all these register ops go away. Right, and you don't even need a special one for reading a particular character from, or particular one of those registers. So the idea of registers is still there, but it goes away. So that whole set went away. But actually, other code depends on that. So I'm just going to use the empty string here. Actually, we'll do it on the next line. So I'm going to make a whole video about this virtual machine and how it works and all that stuff on my main channel very soon for the thing I'm working on. Main big project now. I wouldn't quite call it a startup, but it's a small business I'm launching. So that's all coming soon. So you for now just take my word on it that this all makes sense. All right. So now the control flow ops, f ops. This was halt. Halt goes away. Jump was going to go away, but I couldn't get rid of it. I really needed jump. Then we have hop and hop 0. A jump is a small version of a hop. So a jump takes a jump is a large version of a hop. Jump takes a parameter and jumps to that address. And so it's specifically for when you have a module, rather than when you start, like at the very start of the BIOS, you want to jump to a particular label that's defined way down below. So you want to jump way over all the definitions. Whereas hop takes a byte, and so if I'd only had hop, then you'd have to be able to somehow set the IP address, and that's the instruction pointer, and that's a jump. That's what jump is. So jump assigns the instruction pointer. Hop is a relative jump forward and backwards. So all the control flow uses hop and conditional hops. Call takes an address and does the same thing as a jump, but it also pushes the current instruction pointer onto a stack. And then return pops the instruction pointer off the stack, the control stack. R0 was a conditional return, and that is gone. Eval would take a value off the stack and do a call. So call dynamically, but that can be done by taking the number on the stack, on the data stack, pushing it to the return stack, and then returning, right? But you have to do that from a function so that you have you have like the previous. But that can totally be done. That's going to be a neat little trick. And then next is a operation that I stole from John Ernest's Mako machine, and it basically does the guts of a for loop. So it does a decrement and then a conditional jump. And it's probably way more complicated. So I'm thinking of that as an extended operation that is not part of the core machine, but that that can be built in. So the idea of this machine is that you've got like a very tiny. Like I'm stripping everything to the bone here. Like some of these stack operations might not even be useful, but stripping everything down as much as possible, so that even though it's a bytecode interpreter, there's only like 20 something. I think there's like 24 at the end operations, maybe 25 now that I re-added jump. And yeah, so it's very small. And I think there's an operation for like inspect virtual hardware. So you can send anyway. The point is that it's very small, but you have the rest of that bytecode to play with, right? And like, or not all the bytecode, because like some of it is like message passing. So like every ASCII character is a bytecode that pushes that character onto the stack, and then when you get to the end of the string, you can invoke something that I'm sorry, every character pushes that on the stack and then calls whatever function is in register 0. I'm rambling, but the point is that even after you have all the ASCII characters, then you have a chunk of bytes that represent valid Unicode UTF-8 sequences. You can send it you can just send the machine any UTF-8 string, and it will do something with it based on what the how it's programmed. And so it's a stream processor for UTF-8 text. But then there are characters that cannot be part of a UTF-8 stream, and those are the bytecodes. And so you've only got like so many of those. I think there's somewhere around 60. Or sorry, I guess there'd be 64 plus, I don't know, maybe 68, something like that. No, it's probably around 72. There's like 10 at the end, and then there's like 64 in the middle. And those 64, half of them are reserved for talking to hardware. So so that you'll be able to assemble a virtual hardware, stick it onto your virtual machine, and then now the bytecode from that hardware is able to do things, and you can just talk directly to it through your virtual machine, and including like a network or whatever. You can get basically 32 instructions to directly control the hardware from the stream, and then you got like space for all these extension operations. So some of them are like next, and then read a byte, write a byte, write an integer, read an integer, write an integer from arbitrary places in RAM. And then these are like streaming operations. So this should be XR. It's missing. So read and increment the read from the so you have your named registers, 32 named registers, so letters and a couple punctuation ones. So there's an X register, and if you read from that register with this particular instruction, you can always read from it using read integer. But if you use XR, then it reads from the address. So X, it treats X as a pointer, reads from that point, reads a number from that pointer, and then adds 4 to it. So increments, move on to the next integer in memory. Same thing with Y. Now you've got, if you have 2 parallel arrays and you want to like map the addition operator over them, so like add the 2 arrays together the way J does, right? You say like 3, 2, 1. Whoops. 3, 2, 1 plus 10, 10, 10. That's going to be 13, 20, 13, 12, and 11, right? So you have your X pointer going down this one, your Y pointer going down this one, and then the Z pointer is the same thing, but it increments, but it writes. So, or rather, this operation. So read from X, read from Y. You read an increment X, read an increment Y, and then write an increment Z. And then that's it. What is WP? Write to port. Okay, that is now an operation called IO. I had this notion of so that's still to do, but IO. So I never implemented this. This was an early thought on what talking to those machines would be like, those other machines. But I really do think that they're going to like share the stack and then plugged into your memory. So you get plugged in and you get direct control of the CPU and whatnot. You get to talk to. So the machine. So like if you plug a terminal device into your B4 CPU, that hardware is able to pop things off the stack and like take arguments. If you like the terminal might have an opcode called like go to a particular, put the cursor on a particular point on the screen, and so it takes the x and y coordinates and will pop those off the stack. And so there's like a protocol for it. This is all like theoretical here. So anyway, so memory ops. This is actually, I don't know if IO is a memory op, but there we go, IO. And then DOps is, we'll call it HOps. So this is for dictionary. And I had, in this version of it, I actually have an assembler. And I use this word. So B word, BW is like a begin word, and it was meant to start a definition. I found a better way to do that, in particular that jump operation. So that that version of the assembler is no longer going to work. It was a silly operation. It was only for doing these things, and then what BW did is it set a bit that I called the Skippy bit, and it would, as you're reading through the opcodes, right? This like starts a definition, a begin word, and then the next instruction in memory tells you which of these registers you're defining. And so basically, it takes the current position and puts that into a register, and then turns off execution. So instead of doing the operations, you skip them, right? And then go turns the execution back on. And so basically, it was a silly gimmick to do this, and it was just too silly. So that's going away. So I'm going to get rid of DOps and ROps. I think ROps is only used in this line right here. So we're going to remove those direct access to the registers, and we're going to remove the, I call it something else in remove. So we're going to put this here. So we've got stack ops. Maybe I should, like, this is meant to be like a page of text. So let's do it like this, so you know what they mean. The stack ops, math ops, bitwise ops, comparison ops, flow ops, and memory ops. And in fact, these are actually extended operations. The plan is that I'm going to have an operation called move that does like all of these things. It's going to take like several bytes. It's like a multi-byte instruction, and it's going to decide whether you want to push, if the source or the destination is the stack, and then do you want to increment? Do you want to increment the source? Do you want to increment the destination? And I haven't fully spec'd it out yet, and so these are actually like extended ops. So let's call them EOPS, right? EOPS. And then those are going to be these three. And then hardware, IO is the hardware op. Memory ops. And then IOPS is IO. I call it hardware ops. Hardware IO ops. And EOPS is going to be extended ops, and actually next is going to be one of those. I went back and forth on that. X is an extended op. I think that's it. I think those are the only ones. I might have missed an extended op. And so then we have, just double check these. This would be SNB, SNB, CFMHE, and so I'm missing EOPS. And then OK is an op, but it's written like that. Oh, so we probably actually do need to put that on. So it could be a flow op, and it can be. Oh, but that's not going to work because that breaks the. So we'll call it OK for now. Yeah, this should be op 0, but then we have to explicitly call OK. So I'm not sure we have a test for that. Do we have a test for the no op? I don't think there's a test for that. There should be. No, there is. The debugger does something. When you're testing the debugger, when you test the step instruction, it executes the no op. So all it does is move the thing. So the question is, does it? Oh, we'll see. Okay. Make run. Make run. Yes. Okay. So now, what I changed before I did all that was it is op. If it is an op, then run. If it is an operation, then run the operation and continue. Shift is not working. Okay. Is it backwards? My guess is it's backwards. Yes. So the arguments were swapped. Okay. Right, so now I have an assembler. I'm paranoid now because by changing this list of operations, I remove some things, and when I try and compile the assembler, it's going to tell me that some of these, or when I try to assemble the assembler, it's going to tell me that these ops don't exist. But oh right, okay, yeah, I was worried that I changed the semantics of an op that did exist, but I didn't. I didn't change S shift right or shift left. I made a new op called SH. So I'm good. So that'll trigger me to change the code when I get there. Okay, so that's fine. Now the math and is supposed to dput mask. Where did I have the? I lost my little machine. Let's do this. Let's add an operation. Echo exiting into J. Type main to return. So we do that, and now we say J, we've added this. So now we can say, we can inspect what's going on here. So now we have our VM. Oh, it's actually kind of cool. We can say J, and then we can say dput each, or dput on the levels of on the individual tokens right here, right? So now that's on our stack. If we say dvm, but capital D, and we see that. And then if we type main to go back in, and then we type D, we get that. I like it. That's neat. This is the first time the VM allowed me to do that, because J has the REPL built in, and Pascal and GDScript don't. In fact, that's why this one didn't have a REPL to begin with. It's because I just used J, and I just interacted with it directly. But jumping into the language of the thing allows you to of the virtual machine itself allows you to have a little DSL here. You don't have to type all these underscores for D underscore VM or whatever when we use data stuff. Okay, where am I? It also allows me to put a debugger for one. I can make one nice UI for debugging all of the implementations. That's kind of the idea. All right, so where am I at? So I did that because a test is failing, and the test is this test that AND does not work. So if we say 5 AND does something. The 5 add. Oh, give me syntax. Oh, no, because I'm in J now. I dropped out. 5 add, and then D. The last number should be a 10, which is A, right? But AND didn't work. Something is wrong with the implementation of AND. So we find where AND is. That looks right to me. Because die is a dyad, so it takes 2 operations off this. See where die is, right? Names, names. I guess this is my. So if we say die, y set at dpop. That's bad. This is what die should be. All right, so it did. Okay, but it's not. dy is also the name of it. So this is here. It means this conflicts with dy, but it doesn't because I've deleted that one. So let's where's dy? Right here, and we'll say these are all going away, so it doesn't. So everything in that section. All right, but why does this fail? So AND should be O1B. So if we say 0011 and then 1100, sorry, no, 0011 and then 0, 1, 0, 1. This should be the AND operation, and it should give me back 0, 0, 0, 1. Right? And it does. And what about when we do numeric AND? So we do 15, which is all ones, and do any number, 5. So that should be giving you 0, 0, 5, 1. Domain error. Did something change with the... Oh! It only works for ones and zeros. But if we give it, and so it's 2b, 0, 0, give it the truth table, and then another one, right? That works. And now if we put 5, 15, and 6 over here, we should get 6. Yes, okay, so that's the bug. We need another one here to make them actually do the bitwise operations. And the same, so and, or, and XOR are all that. And then what about not? 26B. 26B. Oh gosh, 0, 1, 0, 1. What is 26 in binary? Sorry, what is 26 in binary? No, 1, no. Yeah, so this takes the left argument. So here's the input pattern for I write it. 0, 1, 0, 1 is the left argument, and then you say not anything, right? It's only going to be it's not X basically. 0, 0, 1. It's going to ignore this right hand side completely. Huh. Oh, but I hard coded the 0 there. So 26B. Right, because it's flipping the sign because it's taking the entire 64-bit number and flipping it, flipping the bits, and then we're in two's complements mode. Okay, so anyway, this is not important. The point is this was already bitwise for an integer. Okay, and it's not a dyad anyway. So I think that works. And I don't run the tests. Okay, so 13 tests. Now we are up to 16. I'm kind of in easy mode on this implementation here because like I've already implemented a virtual machine that's very similar to what's going on here. Dropping exiting the day, type main to return. Let's move this onto its own line so it doesn't run. Return. I actually do have a problem with not, so nt equals not mo. Okay, so nt, so we say we just push the number on there, we push the number 12 onto there, and we should get back negative 13. 12 not. Sorry, nt 12. Negative 4, why? Why would it be negative 4? rather, not 12. Let's say 32 then. -1. 32 shape 2. You would say 8 shape 2, right? So 12 is this in binary, and we say not, then it flips all those bits. Something's wrong here. Why did it put, why is it -4 when I, oh, because it's mask. Maybe? NT, what is NT? So he put mask U pop. What is mask? Yeah, so mask is doing some kind of like bit map. Mask equals take the number mask -12. Mask 12, mask not 12, -13. That's what should happen. What happened? Wait. D put -13. That's putting a -13 onto the stack. Is it the decimal conversion? So hex from decimal -13 is 3. Whereas 13 should be D. All right, so instead of hex, that's the problem. It's a display issue. Hex from decimal, not stack string, but yeah, hex from decimal. So let's put hex. So we'll say hex is equal to, how about hex string? Oh, let's call hex string. So how do you say absolute value in J? -3. So negative, take the absolute value. And we want to test whether it's less than 0. I think you can say star of that and you get a -1, but that doesn't help. So less than 0, less than 0. I'm going to spell it out the right way. Maybe I'll call it. If y is less than 0, do that, but you want to string it up. I will say y is recurse x negative y. Else, that looks funny, x of negative y. how about x modified else some string y is less than 0 to hex of negative y else $, comma, x from decimal. You talking to me? Hang on 1 second. 1 second. What you doing, sweetie? Down in a minute. 2 minutes. I don't know. No idea what she's saying. All right. Anyway, no idea what that little baby was saying to me. How long have I been doing this? 2 hours. I'm at the 2-hour mark, and maybe I do some more in a little while. All right, but I think that's going to work. So hex from decimal y. That's what I had before. I should check this code in as I'm going along. Now I can't do a diff because I didn't. Unless I have it here. I don't know what I had originally said. What is stack string, right? Yeah, whatever. Doesn't matter. Does not matter what I originally said, just matters what it is now. So hex string is this. So upper at hex string. All right. Yeah. X minus y. Why? Value or hex? Oh, hex because it's hex string. All right, that worked. I think we can say so. You should be able to say this, right? That's recursive, right? Yeah. So, oh, that gives you a stack error. I don't know why. Because it's like this. It doesn't refer to the containing expression, but that's like a recursion thing. It's a much narrower in scope than I would like for recursion. All right. So really, we want just do this: x from decimal negative y. A little bit of duplication there, but oh, why is that broken? Oh, because I didn't put the. Right. So now the equal operator is putting a 1 on the stack, but it should put a negative 1 on the stack. So equal is this, but it should be this. And now we've got to change to how operations work. Now I have to actually change them. This actually, we're down to this. This is a way to. This is a crazy way to write 2 definitions on the same line. But maybe we just do right, the ticks, the back ticks, because you're just assigning them. But less than is equal to negative at. These are the ones that are going away. Oops, I I didn't need to do that. All right, so all those tests pass, all the comparison tests are passing. CD and DC no longer work. All right, so CD, that's because CD and DC CD and DC were special things for, all of these are going away. MB bold. I'll just get rid of it. Do I need that? Anyway, these are now DC and CD. So data stack to call stack, and then call stack to data stack. But it's called, well, it's still called rpop and cpop and all that. Rpop query replace rpop with cpop. Yeah. Query replace rput with cput. And the register still is named C and R, but you know, we'll fix that. Okay, so I expect that test to pass now. So we're on test 23 test pass. Let's move up to 24 test pass. And then we're going to put $, and then X from decimal. Oh, right. Yeah, it doesn't have that leading zero. X from decimal of the program counter from VM. Why is that? P of VM -1. But I told it, oh, because jump doesn't actually do that. Jump doesn't take an argument. Jump takes an argument off this. No, jump takes an argument from ran. So jump is not actually the instruction. So we actually just want to say P of VM. So that's not a jump. There we go. And then step does nothing. So step. Oh, it does something. So go into J, and then what is step of VM? Why is it not? VM16B100. Not 100. 256. I hear my baby's daughter crying. So, you okay, sweetie? Oh, it's a little one. Yeah. Okay. I'm gonna wrap this up. I might come back later. So, but I'm wrap this up for now. So thank you for watching, and I will see you again soon.